Alright, so we're going to start talking about projectile motion. And what I want to do is I'm going to break section 3.5 into a few different parts. Part 1 is what we can do and the limits of problem solving. So that's exactly what this video is about, is what we can do and what our limits of problem solving are. And what we're going to do is we're going to focus on what areas we can focus on in problem solving, and how do we establish the area of focus in problem solving and use it to solve problems. Alright, so this is it just kind of takes place over like one paragraph of section 3.5, but I do want you to read it, and then I'm going to break it down kind of by example. And one of the things that's really important for you to understand when we talk about focus and problem solving is nobody has to tell you what the area of focus in problem solving is. Nobody has to tell you you're going to be using this physics concept, or make sure to break it down into this section and this section. Nobody tells you this. It's your job as the physicist and as the problem solver to make sure that you're looking at what the area of focus in a problem is. It's your job. Nobody tells you what to focus on. Alright, so when we problem solve, we have to break situations down by which physics we can apply and when. Right? This is the #1 thing that we looked at as a strategy when we solved problems in kinematics, and it stays true the whole time. All right, so I'm going to back it up a little bit just so we make sure that you can see. Okay, so we're going to start with one example that should be a familiar example, a stopping car. Alright, so we looked at stopping cars when we first looked at kinematics. Alright, stopping a car involves two different physics principles, uniform motion and uniform accelerated motion. Again, I want to remind you, nobody has to tell you this. You're the one that's responsible for figuring out that stopping a car involves both uniform motion and uniform accelerated motion. Remember, uniform motion is when acceleration is 0. Uniform accelerated motion means that you're accelerating uniformly, either in the positive or negative direction. Alright, so when we do this problem, we think finding the total stopping time requires us to solve separately for each section based on the principles involved. Alright, so we have to consider, we want to actually look at the situation of a stopping car. Alright, and then we know, well, when you stop a car, it's broken down into two parts. The first part is your reaction time. Alright, the first thing that happens is you have to realize you need to stop and to decide to stop. That's called reaction time. And it's different for every person, but it's usually just a fraction of a second, and then your body actually acts. Reaction time depends on how quickly the chemical signals fire off in your brain. From the moment that the image of time to stop happens to the time that your body reacts. Right? And for reaction time, right, it's before your foot hits the brake. Right? That's going to include uniform motion, because you're not actually stopping yet. You haven't decided to accelerate. You haven't acted in acceleration. Right? So uniform motion means that acceleration is 0. Right? That's your reaction time. Then, at this moment, until you're stopped, this is called your actual stopping time, your actual deceleration time. This whole time, from the moment that you begin applying the brakes to the moment that you stop, you're experiencing uniform accelerated motion. Your acceleration does not equal 0. Right? And at this point in time, you can actually take this problem that asks you to solve for the whole stopping time of a car. It's going to be the time it takes you to stop here, right? The time that it takes you to react here, and the time it takes you to actually stop. And then the total stopping time will be the time of reaction plus the time of acceleration for your total stopping time. Same with displacement, right? Your displacement before you begin braking and your displacement once you're finally in the action of accelerating. So you get your total stopping distance. Displacement of reaction plus displacement of acceleration will equal your total displacement. So breaking it down into a section of uniform motion and uniform accelerated motion actually allows you to consider, right? Well, when you were moving uniformly, you had this velocity, right? And that velocity should be the same here and here. All right? It was the same because there was no acceleration. That means that you use the relationship of your velocity will equal your displacement over that reaction time. All right, and that will be true under any uniform motion situation. All right, so all you need is two of these variables, and you can solve for the third. You can solve for displacement, will be the velocity times the reaction time, and that would give you the displacement. And likewise, you could solve for the time, would equal the displacement over that average velocity, or your velocity. Alright, so that's what you can do with the uniform motion side, and that's really all you can do for the uniform motion side. There's no other relationship that you could find true when acceleration is 0. That's all you need. In uniform accelerating motion, you know that you start right here. The moment that you hit the brakes, you were traveling some velocity. This velocity is the same velocity you were traveling over here because acceleration was 0. And you know over here your final velocity was 0. So you have some acceleration A that happens here. And now you can use, depending on if you're solving for the total stopping time or the total stopping distance, displacement, you would either use you'd either use a kinematic equation where you're finding the relationship between displacement or time, or you could use a relationship between the velocities and the displacement. It's really up to you and what you're solving. But the connection point here is the moment that you switch over from uniform motion to uniform accelerated motion, and then you use your variables. All right, and this right here, this is a boundary. It's the boundary to your problem where you have a different physics principle that applies over here than the physics principle that applies over here. But the information here is the same for different components of both. All right, and that's your boundary in this problem. Let's take a look at another example. Another example would be tossing a ball in the air. All right, when you toss the ball in the air, right, it starts in your hand. Oh, by the way, this might be Benny's hand, because take a look at this. 1, 2, 3, 4, 5 fingers and a thumb. Terrifying. Speaking of terrifying, look at that sunburn I got in my hands. Just awful. So the ball starts in your hand and you throw it up in the air, and you know that at the point in time when the ball is in the air, you have gravity acting on the ball. All right? But if we're going to analyze this problem in terms of kinematics, the only part of tossing the ball in the air that we can consider using kinematics and using uniform accelerated motion is a time when the acceleration is uniform, and that is the time when the ball is in free fall. That's the only thing that we can consider using uniform accelerated motion. Right? Anytime the ball is not in free fall, there is not uniform accelerated motion. All right? So the ball is in free fall. The moment it leaves the hand, until it's caught or until it hits the ground. Again, remember, nobody has to tell you this. You are the one that has to make this connection, decide what physics principle actually applies, right? And you have to think about it, right? When an object's in your hand, you're throwing it up, which means you're applying a force. You're causing it to accelerate upward. Likewise, when you're catching something, you're applying a force. You're causing it to change how it's moving. You're accelerating it. So in the moments before it leaves the hand and the moment after it returns to hand, those are no longer uniform accelerated motion. That means that that's a boundary. All right, all we can consider is this free fall motion up here. All right, problem-solving boundary is where uniform accelerated motion does not apply. That's a little bit nicer. All right, when the ball is being thrown upward, other forces, non-gravity forces, are working, and the acceleration isn't uniform. All right, that's important because not only is acceleration not uniform, but acceleration is not 9.8 meters per second squared toward the center of the earth when you're throwing the ball up. How do we know that? Because the ball moves in a positive direction when you throw it upward. Right, that means you exerted a force in that direction. You caused an acceleration in the up direction. That's not acceleration due to gravity, so you know that that's a boundary. Likewise, when the ball is caught or hits the ground, if gravity is the only force acting on the object, then the only acceleration we'd experience is 9.8 meters per second squared toward the center of the earth. If you're stopping the ball from falling toward the center of the earth, you are applying other forces and you are changing the acceleration to a value other than 9.8 meters per second squared toward the center of the earth. All right? So the truth is that we can still solve for the situation where the ball is actually getting thrown up, and we can solve for the situation where the ball is hitting the ground. It just requires different physics principles to solve. It's not uniform accelerated motion, so we cannot use our kinematic equations for uniform accelerated motion in those moments. We would have to use something else, and we will learn that something else. It's forces and dynamics that we'll be looking at, and also energy. But the boundary of using uniform accelerated motion is the moment when the uniform accelerated motion is caused by the motion of free fall. That's it. That's our boundary. That's all we can solve for. So the good news is once you start thinking about the concept of breaking a problem down and solving it with appropriate physics concepts, it also applies to projectile motion, our new concept. And remember, nobody has to tell you to break a problem down. Nobody has to remind you to use appropriate physics. That's your job as the student. That's your job as the problem solver. You have to decide where the boundaries are, and you have to decide what the appropriate physics concepts are, and then you apply them and solve the problem. So we're going to be doing that for projectile motion also, and we're going to talk about the boundaries of projectile motion. The process of an object being thrown or projected is not uniform accelerated motion, so we don't ever consider it with the physics principles of uniform accelerated motion. All right, so if you're literally in the process of throwing an object, if you're literally in the process of catching an object, some force other than gravity is acting. You're speeding it up with your own muscles. You're slowing it down with your own muscles. Therefore, the motion is not uniform and accelerated, so we cannot use kinematics. Right? Throwing and projecting are not free fall. They're other forces, and we would solve them using concepts with other forces, which we haven't learned yet. So that means that the throwing and the projecting action are not going to be a part of what we consider when we solve projectile motion problems. When we solve for projectiles, what we do consider is we consider a focus only on the motion after it's been projected and before it's landed or caught. So it's very similar to the boundaries of a free fall problem. Right? We don't consider when it's in the projecting or throwing device, and we don't consider when it's actually in the process of being caught or hitting the ground. We only consider when it's in free fall. That's it. Because when the object is moving freely through the air under the force of gravity alone, we call that free fall. All right? And when the only force on the object is gravity, the only acceleration of the object is gravity. And it acts toward the center of the Earth with a magnitude of 9.80 meters per second squared. And we can assume uniform accelerated motion, and we can calculate using our kinematic equations for uniform accelerated motion. All right, so I really want to re-emphasize that for you guys. It's one of the most important takeaways for solving projectile problems. We're only focusing on the time that the object's in free fall. Because when the object's in free fall, the only acceleration that we have to worry about is acceleration to gravity, which is always down, always toward the center of the Earth, and always a magnitude of 9.80 meters per second squared. So then we can consider projectile motion using kinematic equations. And that's what this section, that's what this chapter is really all about. And that means that we can take this information now and we can solve for projectile motion.